What's that? 5 minutes. I was worried, like, is this talk gonna last for an hour? That's a long time. Just saved me 5 minutes. All right, so topic of today, OPA everywhere, exploring the OPA intermediate representation or IR format. There's gonna be a lot of things covered here today, so buckle up. First off, I'm Anders. I work as a developer advocate at Styra, which is the founders of the Open Policy Agent project. I have a quite long background in software development. For the last 7 or 8 years, I've been working primarily with identity systems. So basically proving who you are in various digital systems. That eventually led me into OPA. So when you're in identity and you work for identity vendors and your customers come up and they're like, okay, identity is solved here. What do we do with that? We know who the user is. We have these attributes. We might have some roles. We might have, how do we use them? That's our authorization, right? And as an identity vendor, the standard answer is pretty much like, that's not our problem. That's your problem. So great. So after 7 or 8 years, I got curious. Like, what if that was my problem? So I kind of dropped out of that company, started working at a corporation where we had teams working in 12 different countries, 8 or 9 different programming languages, so pretty much the whole spectrum. And we had to solve authorization across that tech stack. So how would we do that? That's how I ended up, or that's how I found out about OPA. And I've been working on the project for, I think it might be 4 years now even. So first as an implementer on the kind of user side of things, and for the last 2 years at Styra. And when I'm not working with that, I like cooking, food, and football. If you want to reach out later, I'm just my first name and my last name on all these channels. All right, so back to the problem. How do we do authorization in distributed APIs? Because that's basically what I had to work with. Modern tech stacks increasingly tend to be distributed. And that's a pretty complicated problem. But first off, since my background is in identity, I figured like maybe we can start there. So basically the monolith model, as at least folks as old as I am have some experience with, it's basically the transition to microservices, basically just the same responsibilities, but rather than function calls, we have network calls. And what we're in particular interested in today is, of course, authentication and authorization. So in the monolith architecture, it's a rather simple model. You have one application that basically does everything. The user provides some credentials, the application set up a session, it obviously checks the identity of the user, verify the credentials. Once the credentials are verified, we check, is the user allowed to do this operation? And if the user is, we send back some data or we allow the operation. In a distributed application, however, authentication is commonly delegated elsewhere. But up until now, we have not really had a good model for working with this in distributed architectures. So if we were to make it a fairly naive translation of the kind of monolith architecture, we were to just translate what we just saw into a distributed architecture, it would look like this. We'd have any number of services that all did all of these things. They'd have to verify credentials, they'd have to verify permissions, and eventually end up at some data store where we, if everything looks good, we send back the data to the user. So there's a couple of problems with this model once we go distributed. And the first one is, of course, it's pretty obvious for security-minded people, which is, of course, like passing around credentials. The users may have submitted like a username, a password, or whatnot, but there's really no reason that each of these services should know about the user credentials. And it's an obvious risk of information leakage and whatnot. So that would be the first problem. The next problem, of course, all these red arrows. Once you start to add services and they all need to verify credentials, you have a lot of requests going to the user database in order to verify those credentials. So rather than passing around credentials, we delegate that responsibility to an identity system. That was one of the kind of great ideas with where identity systems kind of tend to scale with any number of services, because the services are no longer concerned with verifying credentials. So the user verifies, or the identity system verifies credentials, and if you're good, pass back a token, and that token is carried across all these services. So no passwords, no nothing in our services. And of course, everyone now wants a token, because that's really the keys to your system. So how do we obtain one? That's basically what OAuth does. OAuth is a protocol which defines a set of flows. So whether you're a robot, you're a human, you're a mobile device, or an IoT device, there's a flow for you to obtain credentials so that you can access these systems. What's interesting about OAuth, it's all about tokens. And that's really all there is about OAuth. And at the same time, OAuth says what a token is left as an implementation detail. So it doesn't ever say what a token actually is. It's just page after page after page about how you obtain one. Once you get one, it doesn't say what it actually is meant to be. Another interesting fact about OAuth, it's labeled as an authorization framework. It's like in the heading, but it's not really about authorization. It's very little around OAuth revolves around authorization, like checking claims or attributes. There's a basic feature of scopes, which is basically saying this token is intended for this or that system, and it can only be used for those systems. But that's about as far as we get. Another thing OAuth doesn't say much about is, who is this fella? So OpenID Connect added an identity layer on top of OAuth, providing things like, here are some standard claims that we can expect to find on a user, email address, phone number, whatnot. And another issue here, these tokens. If OAuth doesn't say what a token is, how would we know? How do we verify these tokens? The naive model, again, is, of course, if you get a token, it just says ABC 123. How do I know what that means? That's what we call an opaque token. In order to verify that token, I don't know what it means. I need to ask someone else. I need to ask whoever issued that token. So I need to go back to the identity system and say, is this a valid token? What user does that represent, or what client? And of course, we're kind of back here at the original problem. Now we just kind of pointed our arrows elsewhere. But if all our services need to go back to the identity system and ask, we still have that problem. So that's kind of the invention of the JSON Web Tokens. There's been a few other formats for doing this, but the main idea is largely that the tokens should be self-contained. So any data that we might need to know about this user or the client should be contained in the token. The token is digitally or cryptographically signed, so we can verify the token without reaching out. All we need is just a public key. We can verify the integrity of the token without going to an external service. So with JSON Web Tokens or any other kind of self-contained token, we solved that problem as well. We have a good model for working with identity across distributed systems. So that's good. How do we do authorization? So the naive model, again, back to this kind of monolithic model where all our application would just send a request to a database somewhere. That doesn't scale well when we have hundreds or thousands of services and each of them wants to check permissions. It doesn't scale at all. And of course, if you're in a company like I was at, the permission database is on a mainframe somewhere, and it's far away from this modern cloud environment where we wanted to build our new system. So those requests were super expensive. And we have another few problems here. All our authorization logic is embedded in these applications. It's a problem we will deal with in a minute. But first, how do we solve these kind of red arrows? And where should we do authorization? So this is kind of the cheap way of solving this. It's a bit of a shortcut, but it's been a very popular shortcut for the last 10 years or so. It basically says it's expensive to do these checks, so let's just do them once. Let's just do that in a gateway or somewhere in the perimeters of our systems. And once you pass the gateway, it's an open highway. It's too expensive to do these checks. We can't, but we know that the request must have passed the gateway. Until, of course, that breaks somehow and somebody manages to pass the gateway. But the good thing about it is really fast. There's only one lookup per request. It, however, provides a single point of failure. If the gateway is down, everything goes down. It's insecure, of course, because if you do manage to find a way past the gateway, there's basically no access control. It's just everything just assumes that the gateway must have done that for us. So the basic premise of the zero trust model, it says this isn't good enough. And if you're in a regulated industry, it's probably illegal. You can't just ignore access control like in your backends. You have to do it everywhere. But it's slow. If you were to do it, we're kind of back where we started, aren't we? So we can verify the identity of the user for sure. We have that in the JSON Web Token. But that doesn't tell us. It just says this is the user. This is the role. It's a developer. It's an admin. But it doesn't say what a developer is allowed to do or not. So again, we're pretty much back where we started. The good thing about the model is that it's secure. It's slow, but it's secure. So how can we improve on this? I don't know if you all noticed, but the kind of direction of the arrows here just got flipped. So rather than having all of these services query the database for permissions, a common solution to this is to rather have the database push those permissions to any service that might need them. So your services keeps a copy or a portion of the permission data in its memory or on disk, so you don't need to do these online lookups. And this is surprisingly effective. It works really well. The case where this might break down is, of course, if you have like hundreds of gigabytes of data, and you need to push that to hundreds of services. That's going to be expensive and so on. But for most kind of deployments, this is a fairly good model. So we kind of scratch the slow thing here. We don't have a single point of failure because even if the database goes down for a few minutes, each service has a local cache of the data. So it might be slightly stale, but it's still going to be up and running. We still have authorization logic embedded into our applications, though. It might be another problem. Again, coming from where I did, in this organization where we had microservices in, I think, 7 or 8 different programming languages. and someone says, how do we solve authorization? And we had a fairly advanced set of requirements, fairly advanced set of policies. So of course we can go to the Python team and say, here's our requirements. It's going to be like 20 pages of requirements. And we bring that set of requirements to the Java teams, to the .NET teams, the Clojure teams, the Go teams. And what we're likely going to end up with is, of course, 7 entirely different implementations of those requirements. So that's really hard to get right. And each of them is going to have like their unique set of bugs, unique set of misinterpretations of the requirements, and so on. And of course, so this is going to require some coordination between the teams. But worst of all, if you're in a regulated industry, how do you audit this? If somebody comes to you 3 months later and they say, we had a breach here 3 months ago, we don't know where, but somehow some user got access to some data that they were not supposed to. Right, how do we audit this system? We have 7 different implementations. They all do audit logging or decision logging in their own unique way. They all have their own unique implementations, their own bugs, and so on. How do we audit that? Well, you can't. So that is one problem that still remains. We have authorization logic embedded inside of our application. If you have an entirely unified or architecture, like we only have like Java in our organization, whatnot. This might not be as much of a problem, but eventually I think it will be. And I think like with one of the clean benefits of microservices is basically that it allows a greater level of team autonomy. So one team should be able to make decisions on languages or frameworks without having to ask around what's the blessed one in the organization. So I think this type of organization is not uncommon, it's not unique, it's basically where most of the industry is moving. So OPA, finally, what is Open Policy Agent? It's an open source general purpose policy engine. It provides a unified toolset and a framework to work with policy. And when I say policy, it basically just means a set of rules. So anywhere you have rules, and of course, what is authorization if not rules? That's basically what authorization is. It just says if you are a doctor, you can retrieve the medical journal of your patients, but not of some other patients. That's basically a policy, right? And the policy is a set of rules. But it doesn't have to be access control. It could be policies around infrastructure. It could say you can't deploy on Fridays from the pub, or you can't provision S3 buckets unless they have this or that security configuration, or you can't say kubectl apply on some resource where it's not properly labeled with a team name or whatnot. So policy is a broad topic. We'll mainly focus on access control and authorization today. But OPA does not, importantly, it's a general purpose policy engine. So it does not decide. This is the use case for you to use this tool for. If you want to use it for all of these purposes, all the better. So one kind of key item with OPA is this idea of decoupling. And for me, as an identity nerd, it's basically what I came from. Remember how we kind of decoupled identity? We moved that to a separate system. And we said, like, the user can go there and do this. So we didn't have to deal with that in our services. And even if you're not an identity nerd, you probably like that concept. Like, I don't have to deal with this anymore. We just delegated that to some other system. That's the best thing you can do. You just delegate, delegate, delegate. You got a lot of tasks here. Just send them elsewhere. So that concept of delegation or decoupling is a key concept of OPA. So we want to kind of break out the policy or the decision making and move that out from your application. And that's basically the only way we can do that in a unified manner if we have microservices in all these different languages. We separate policy decision from enforcement. It's another concept of OPA. It basically means OPA makes decisions. It says, this user should not be allowed based on the input I got here. But it doesn't do anything with that. It's just going to tell the service. And then it's up to that service how it should act on that. Policies, they're written in a declarative language called Rego. We'll take a look at that in a few minutes. And again, since it's a general purpose policy engine, we'll see use cases like Kubernetes admission control. And I'm sure a few of you have used it for that purpose. Microservice or app authorization, infrastructure, data source filtering, CI/CD pipeline policies, and much more. So to kind of summarize the project in the tweet from Kelsey Hightower, the Open Policy Agent project is super dope. I finally have a framework that helps me translate written security policies into executable code for every layer of the stack. That's basically what we're all about. So how does it work? How can it work with like so many different technologies and so many very varied fields? I think like one key to that is basically this. It's a policy decision model. It's a very simple one. It kind of has to be in order to integrate with all these systems. So we basically have a service. That could be our microservice, or it could be anything really. It could be a Kafka broker. It could be an API gateway. It could be a Linux PAM module. It could be, what have you. It could be basically anything that services a request from a user or a client. When we receive that request, we say, hey, rather than trying to decide whether we should allow this or not, I'm going to delegate that responsibility to OPA. And I do that by sending a policy query, basically saying, I have this user, I have this data, and I have this endpoint or this resource, this action, should we allow that or not? That query is just a piece of JSON data. So OPA, it takes a look at whatever policy we provided it and potentially some other external data. It makes a decision and it responds with a response which is also just JSON. And of course, any service written in the last 20 years or so has a JSON parser, or JSON marshaller. That's basically how we communicate between services. And most of these services talk HTTP and REST. So it's a very simple model, but it works surprisingly well across a whole set of systems. So as for running OPA itself, it's a self-contained, lightweight binary. I think it's like 50 megabytes or so fairly lightweight. So ideally, again, we're talking about distributed system here. So it's not like you have one big OPA server running somewhere. You will have hundreds of OPAs. For each instance of your application, you're going to have at least one OPA because you want these decisions to be fast. You don't want to go a long distance to query OPA for decisions. It should be as close as native as possible. So that usually entails that you run OPA on the same host, either as a daemon or maybe a sidecar if you're familiar with that from Kubernetes. And applications commonly communicate with OPA across a REST API. There's a Go library available for Go applications. There's Envoy, Istio integrations. There's WebAssembly, intermediate representation, and those are some of the topics we'll explore in a bit. Just going back here to the topic of policy, these policies are written in a declarative high-level language called Rego. And again, a policy consists of any number of rules, exactly as what a policy is in real life. And these rules, when evaluated, they return JSON values. So that could be a Boolean one, which is pretty common. You're going to ask, should the user be allowed or not? It's a true or false, a Boolean decision. But it could also be an object where we say, no, because the user must have this or that role in order to do this. Or it could be a set of obligations. You must first pass this or that. You must first log in using a multi-factor authentication or whatnot. So OPA comes with a unit test framework, because of course, policy is code. We treat policy as code. One of the virtues of code is, of course, that it's testable. And this is even more important when you're dealing with these type of policies. It's a fairly well-documented project, I must say. I've done a lot of that documentation myself, so I guess I'm biased, but I think we have reached a pretty good level of our documentation. There's also a playground, so you can try it out without having to download anything. So how many of you have worked with OPA or Rego in the past? Okay, a few hands, but that's good. Because we're gonna show here. I think I'm gonna have to zoom in here. Still seen? So what we're gonna do here is we're gonna write a simple policy just to kind of get a feel for what the policy language looked like and so on. So I'm just gonna save it as a policy.rego. The first thing we do is we provide a package. I'm just gonna call it policy. So this will be similar to a namespace or whatnot, which you have in other languages, or maybe a module or whatnot. So we have a package, we have a policy. What is a policy? It's a series of rules. So the first thing we likely want to do here is we want to offer a rule. We might call that one allow. So the anatomy of a rule, it's basically this. It has a name, and it has some condition that needs to be if the rule evaluates true. Or let me rephrase that. So a rule is basically a conditional assignment. So if everybody knows what assignment is, so you might say allow is true. It just means we assign the value true to the allow rule. But rules are conditional, so it means allow is true if we write it like this, if, and then follows the conditions, which all need to be true in order for this value to be assigned. So you can basically think of it as allow is equal to true if, and then all the conditions in the block. So if we were to do like something very silly, which we know to be true, and we go back here and we evaluate this rule, we say OPA eval, and we say policy, Rego, data, should I make that bigger? Oh, I missed. I'm just gonna make that prettier. Let's call that pretty. Okay, so now we evaluated that. We know that 1 is equal to 1. So when we evaluate the allow rule, we know that's gonna be true. If we add something else here, and which we know is not true, and again, one thing to note here is that these conditions, they're ANDed together. So in order for the rule to evaluate to true, they all need to be true. So you can think of each line here as having being ANDed together. So what now? We have the rule should no longer be true, right? Because we know 1 is not equal to true. So what we get back here is nothing. It didn't say false, it's just nothing. So when you evaluate the rule and it's not true, it's like an empty void. So what we commonly do here, we say that by default, allow should be equal to false. That's a pretty reasonable thing to want in access control, right? If you don't know how to do something or it doesn't check out, just fall back to false. That should not be possible. Now, of course, in a real scenario, you wouldn't just compare integers of known values like this. You'd probably want something from the service. The service sent us this request, so we probably have some data to deal with. So what I'm going to do here is I'm going to mock what that might look like. Again, input is just JSON. So let's create some JSON. We might have a request. And that request probably has a method. This could be a get one, or the request probably has a path as well. And that would probably look something like users, Anders. I'm gonna simplify this a bit here and make that an array of each path component. I think that makes for an easier data to work with. Okay, so we have a request. We have a GET request to the user's endpoint where somebody is trying to read my data. And of course, we have a user making this request as well. So that user has some ID. I don't know, ABC123. Again, an opaque value. Can't really use that. The user might have a name as well. So that user is Jane. So Jane is trying to read another user, which might be fine. So we're basically going to change this here, and we're going to use the input. So input is it's a global variable which we can reference anywhere from our policies. And we use like a common dot notation in order to do that. So we just say input dot request is equal to get. And in this case, if we save this by now and we evaluate it, it's going to be true because that was a get request. But it's obviously going to be true for any GET request. So we might say that if the input path component is equal to users. So if you're only reading on the user's endpoint and there's no more data provided, you're basically trying to list all the users. So if we just remove this here, we could say that this policy should allow it. Anyone can read, just get the list of users. So let's see if we are allowed to do that. No, we're not, because I did not provide. Did I? Oh, thanks. That's good. Oh. Method. Yeah, sorry, that wasn't a question. It was someone with good eyes noticing I mistyped the path here. So you're absolutely right. So we want to check the request method, which is it's equal to get, and that the first path component is equal to users. And now with input provided, we see that yes, OPA made that decision. It says yes, this is true. So what if it's a put request or a delete request? What will we do then? How do we add more rules? Well, we just repeat what we just did. We just say allow, it's equal to true, and then we add more conditions. So inside of these blocks, the rule bodies, we AND together the conditions, but outside of it, we OR them. So if one of the allow rules is equal to true, we say that the rule itself is true. So if input requests, let's see if I get it right this time, is equal to put, then we might want some more conditions to be true. I don't want the user Jane to be able to modify my user or somebody else, but she should be able to modify her own data. So we're going to say input request path 0 is equal, or the first path component should be users, and the next path component should be the input request username. So we're basically saying if this is a put request, it should be allowed if the path component corresponds. So if this component here corresponds to this value down here, we should let it pass. We're going to have to change the method here in the input as well. There's a typo again. All right. God, sloppy. Oh, you solved it. So also a good demonstration on why you want unit tests of policies, right? So if we are now to change this, the input here, so our user Jane here, she's trying to modify my data. We see that that's no longer allowed. So that's a really quick demonstration of Rego, just for you to get a sense of like what policy offering is about. Policy is, again, a set of rules. Rules are basically just primitive assertions on things like this. So it's basically a more convenient way of writing like if-else statements, but it's kind of tailor-made for that purpose, where you kind of flip or invert the logic. And you first say allow is true if, you don't say if this and that and that conditions, because that's kind of the heart of our problem. If you were to write it like that, you'd end up with really long if-else statements and then just a tiny little assignment in the bottom. So we kind of inverted that, but for most developers, this should be fairly familiar, at least given some time. But again, of course, Rego is much more than this. We have like 150 built-in functions for doing things like JSON Web Token verification or decoding, string manipulation, whatever you might need in order to work with an advanced set of inputs and advanced set of policies. All right. So what do we do? Again, we know what OPA and Rego is. So that's good. We now kind of injected that inside each of these services. Data from permissions, we might still need data in order to make these decisions. That's propagated out to OPA. We solved all of these problems that we set out to solve. We no longer have authorization logic embedded in our applications. So we can write policy from one place and deploy it to all services in the stack. They might be written in any number of languages. It doesn't matter because we have one unified way of working with policy across our whole stack. So distributed authorization solved pretty much. And of course, one change I did here is in a real world scenario, you probably would not have a database pushing data. You'd have something like a control plane or a service that would do that for you. So it would fetch permissions from the database. It would also fetch policies, distribute that to OPA. So you got this kind of nice decoupled model where a change to policy does not mean that you have to redeploy your applications. That's just an asynchronous process which goes on and on and on and on. These applications have no idea what the user is, what a role is, what permissions are required. That's dealt with by OPA. Yes, Christian?
If you have a more complicated policy where you need a lot of data to make decisions like relationships between objects, who would be responsible for that, service or OPA?
Yeah, preferably OPA. Since if you have a lot of complexities in your policies, yeah, of course, we showed like a trivial example of a policy, but there are policies that are like 5,000 lines of Rego. So there are certainly examples of advanced policy. But if you have that type of advanced policy, just means like if you were to do that in your services, then you're going to have to solve that in all these different systems. And the more advanced it gets, the harder it's going to be to do correctly in different systems. Okay, quick advertisement, Styra, that's the commercial control plane. That's it. That's the end of the vendor pitch. So, okay, we solved authorization for 95% of all deployments. If you came this far, you're in a good place. And most organizations are nowhere near this place. But even if you came this far, there might still be some issues. How does this perform? And for the absolute large majority of deployments, it's good enough. So any overhead we might have had before, where we used to query the database or query something elsewhere, that's gone. What we do still have, if you're all familiar with Kubernetes, I guess these would be pods. So you'd have one container running your application, and inside of that pod, you'd also have OPA. That's the pattern which is called like the sidecar pattern. And when you run two containers in the same pod, they will run on the same host. So when you query OPA, that's going to be on the local host interface. So while there is a network call, it's questionable if that can be really considered a network. But it's still like a REST call to OPA. So whatever performance penalty that it is in that call, it's going to be contained inside of our pods. So no longer these arrows on the outside. So the absolute most common model, and it's just this Java here, but it could be any programming language. We're now inside of the pod. We have a Java app or Python app or whatnot. It's sending queries inside of the pod on the local host interface. That's going to be pretty fast. I think the overhead of that operation is commonly a millisecond or two, which again, it's fine for most applications. And why it says 1 to 50 here is because obviously not everyone is running Kubernetes. There might be examples of where you just can't run OPA on that same host. So you might need to go elsewhere to get a decision, and then like the overhead is quickly going to add up. But again, 1 millisecond, is that so much? Not really. For your basic like kind of banking app or whatnot, it's not going to matter. But if you have hundreds of services all kind of included in the chain of requests, and they all add 1 millisecond of latency just to do authorization, well, then you have hundreds of milliseconds just for doing authorization. So how can we solve that? One way of approaching this is WebAssembly. OPA allows you to say, OPA build, I want to take this policy I just wrote, and I want to convert it or compile it to WebAssembly. Then I can take that compiled WebAssembly and I can run it in any OPA or any WASM runtime. This is going to shave off some latency. It's still a runtime, so it's not really native, but it's getting closer. And of course, web browsers. That's the most common runtime, the most well-known runtime. Everybody knows WASM is originally found in web browsers. But most languages today allow you to integrate with a WASM runtime. So if you're running, I don't know, .NET or whatnot, you can, rather than query OPA over a REST API, you can have that policy evaluated inside of your WASM runtime. It's gonna be a somewhat faster model, but it's gonna be way more complex because you can't just pull out that policy and see what's going on in there. If since OPA is written in Go, and your application is written in Go, then you have the benefit of just you can integrate it as a library. And then we're back to where we started with the monolith one. We just have a function call. Can't get much faster than that. So there's basically no overhead at all in terms of the request. It's still going to take some time to evaluate the policy, but that's unavoidable. So our integrations options here, and this doesn't mean like this is worse and this is best. This is only in terms of latency. So obviously, the further we get away from a service, the longer it's going to take. Wasm runtime is going to be somewhat faster, but best of all is, of course, if we can have a native or integrated solution. But of course, not any service is written in Go. So in terms of speed, native integration is what we aim for. But of course, not everything is about speed. There could be some other interesting things when we go native that we can't really do with OPA today. So a few requests that I've had gotten recently is like one from, I think it was Volvo, where they want to run OPA in cars, which is like terrifying. See all some of my typos there, like, wow, you want that in cars? But it was apparently not for the steering system. It was like just something else. So I said, no, we probably can't do that. It's like super limited what kind of architecture they have, like very limited memory and so on. So no, we can probably not run OPA there today. Can we run this on this microcontroller? No, can't. So like a binary, it's 50 megabytes, and you only have like 2 megabytes, I don't know. Can we run OPA inside of the Linux kernel? Which is like C? No, can't. And so on and so forth. We can't really go native with OPA. It's like for most of these kind of Kubernetes and like these type of deployment, which I'm sure most of you will be working with, it's fine. But there are a few of these kind of more extreme requirements where we can't really run OPA today, which is a shame. So can we have OPA everywhere? Yes, we can. So since I think like 5 or 6 releases ago, and we released monthly, so it's basically half a year ago, a new feature of OPA is that we can, in addition to WASM, we can generate an intermediate representation. And from the Wikipedia article on the topic, it says an intermediate representation is the data structure or code used internally by a compiler or virtual machine to represent source code. And IR is designed to be conductive for further processing, such as optimization and translation. That sounds like what we're going for, right? So a good IR must be accurate, capable of representing the source code without loss of information, and independent of any particular source or target language. Great, that's what we want. We want to be native, independent of any particular source or target language. So this seems like it's it. So since 6 months ago or so, you can additionally say, I want this policy compiled to an intermediate representation format. An intermediate representation format is basically an evaluation plan. The problem is, that's just what it is. It's a plan to how would you evaluate this? It's not going to evaluate it for you. There is no evaluator. So that's basically up to you. That's entirely up to the implementation. And we did not provide a number of implementations, at least not at this point in time. So it entails a whole lot more work to get this working. But if you do take the time, you can achieve the same overhead as a native Go integration, which is basically not. So how does it look then? There's a pretty common rule in Rego. It says if admin is in input user roles. Should be familiar. We didn't look at the in operator, but I think it's fairly obvious what that does. So if the admin is in the set of the user roles, we should allow that because the admin should always be allowed. So translating that into an intermediate representation format might look something like this. It's basically just a very low-level set of instructions going from top to the bottom in a very procedural fashion. So OPA itself and Rego is, again, it's a declarative language. So when we had that rule first, we checked for a GET request, and the other one we checked for a PUT request. Which one would be evaluated first? We don't know. It's a declarative language. It's not read from top to bottom. That's entirely up to OPA to decide. And it could take any number of optimizations or have any number of reasons for doing what it does. So it doesn't really follow. And one of the reasons why we can't just rewrite OPA in another language is basically there would be a million lines of code in each of these implementations. Well, if we do have something like this, which isn't unless you're familiar with compilers, this isn't really readable. But it makes perfect sense for a computer. It's just, first, I'm going to clear the third location here, and the next step, I'm going to reference input.user. The next step, I'm going to reference input.user.roles. In the next step, I'm going to assign the value of that to location number 6. And in the next step, I'm going to make a call to internal member 2, which is a cryptic way of saying in. So I'm going to make a call, and that's going to return either true or false, and I'm going to assign the result of that to target number 3. So it's basically just going from top to bottom, and while this might be hard for us to kind of read and reason about, the implementation in code is fairly trivial. It's just implementing the basic commands here. It's going to be a few hundred lines of code. And of course, if you want to implement all the hundreds of built-in functions OPA provides, that's going to be way more. But just to get something working, it's a fairly trivial implementation. So the evaluation plans, they're not really in an Excel sheet, surprisingly, but they are in a JSON format. So in order to build one, you just say OPA build. The target should be a plan, and you need to provide an entry point. You need to tell the compiler where should we start evaluating, or where should I build this plan from. So I think we're running out of time here, but so a high-level comparison of these kind of different models. Again, in Rego, we have a declarative model. In the IR, it's entirely procedural. In WASM, it's compiled into bytecode. For Rego, we have Rego, obviously. The IR is in a JSON format. WASM is in a binary format. OPA has apparently 160 built-in functions. The IR has none, because it's you that write that implementation. So presumably, you're not using 160 different built-in functions. So it would make sense to start with those that you actually make use of. WASM, on the other hand, ships with most of these compiled. So management features, there's a whole bunch of those in OPA as well. Like, how do we pull down bundles of code and policy from remote endpoints? Where do we send decision logs and so on? OPA has a whole bunch of nice features for managing that at scale. If you're running the IR or the WASM version, you have nothing. Again, you need to build that yourself. And in terms of deployment, we saw the server model. It's an external one, even if it's running on localhost. While the IR one, we can integrate OPA or policy inside of our application. So we basically achieved the native requirement. And performance, of course, it's going to vary widely depending on your implementation and so on. Another nice thing with the IR, and a limitation of WASM is really that WASM by design is meant to be sandboxed. So if you want to do HTTP requests, you want to read a file or something, that might not be possible. So of course, if you are to write your implementation, the first thing you want to ensure is, of course, that the one policy evaluated in OPA evaluates the same way in your implementation. That's going to be like the key, the most crucial thing. If that doesn't hold, performance doesn't matter. If you get a different result in your own implementation than what OPA would provide, it doesn't matter if it's like if there's no overhead. So what you want to do in order to test your implementation is, of course, You'd rather, is there a test suite or something? And yes, there is. So OPA comes with its own test suite, which is luckily provided as a whole bunch of YAML files where kind of Rego is embedded. And that Rego we can extract and build into IR. And that way we can run the same tests that we run in OPA in our own custom implementation. And if you're interested in building one, we have a repo for compliance. If you're not interested in building one, what can you do? Well, luckily, me and my colleague Johan, we started just as this kind of format became available. We were like, dude, we're gonna do something with this. It seems like a lot of fun. So we wrote the JARL project, which is a parser and evaluator for JVM, or in Java or what have you, and JavaScript's environment. So it's written in Clojure. So it means we can target both of those platforms. I think we support at least like 110 or so built-in functions already, and more to come. We're already passing like 1,200 tests in this compliance suite that I talked about before. It's really, really fast. So that's cool. One thing, of course, we've not got into the management features at this point, so still a whole lot of things to do. So the CLR, which is the .NET runtime, that is another possible future target via the Clojure CLR project. So hopefully we can add that to the list as well. And we still haven't kind of published this. The source code is out there. If you want to run it and try it out, you can do so. But it's definitely not production ready. But it's getting there. And I think like one of the nice things with doing this in Clojure is like that you get all these kind of deployment targets. You got the JVM, you got CLR, you got JavaScript. So we're not covering all of these languages or so, but quite a fair amount of them. All right, so wrapping up, the standalone service, again, 95% of you, maybe all of you, are probably best serviced by this decoupled REST HTTP model where your service just queries OPA for decisions. But the IR offers a compelling alternative when the requirements demand it. And that could be native performance, but it could be other use cases as well. You want to run OPA inside of the Linux kernel. You want to run it in a car. You want to run it everywhere. So JAWL is the first implementation, which is for the JVM, JavaScript, eventually CLR. Hopefully, many more will follow. I know there's work in progress for a few ones, both like open source and commercial ones. And if you want to learn more about OPA, there's the Styra Academy, which is a great learning resource. We have time for a few questions. Yep.
How does this relate to or compare to the old segment of Alpha?
Yeah. Yeah. No, that's a good question. So the question was, how does it compare to SACML Alpha, which is, for those who don't know, it's an older authorization standard. I think it's from 2001 or so. So and at least originally it was all based on XML. So you define your policies in XML. Like at that time, if you were around, you know, like everything was about XML. If it wasn't XML, no, like don't touch it. It's like you just want to do everything in XML. And then once JSON came along, XML kind of turned into pariah. And so they eventually tried to kind of shift over to JSON and other ways of expressing policy. Nothing wrong with it. I think it's just they kind of came before the advent of JSON. They came before the advent of like highly distributed systems. Their model pretty much builds on this idea that you have one big server that everyone goes to. They have tried to evolve and so on, but I think they're largely playing catch up at this point. But they have played an important role in authorization in the past.
Doing
authorization based on a path or a URL externally from the application is pretty difficult because any path traversal vulnerability will allow you to bypass
Yeah.
the authorization, especially between all the servers. Is doing authorization based on path like we did in the example, is that a production way of doing things, or is just an example?
Yeah, no, it's an example, and I think like things like path normalization and the question was like doing authorization only based on like the path like we did here could be problematic because path traversals and whatnot could make that problematic. But I think that we do that in OPA, it's still there could still be other places where we kind of normalize paths or make things like kind of just as I provided the path here in the form of an array rather than just having like the raw string. So that would obviously mean that we'd need to pre-process that somewhere else before. And I think that's probably where I would trying to normalize and whatnot that would be needed in order to avoid that.
But the Python, Java, and the PHP will normalize that differently.
Yeah, that could be true. That could be true. Yeah, and if we were to do it in Rego, yeah, that would probably make things easier. But it's hard to say without like knowing exactly what specific problem we want to solve. But let's talk later. Okay.
So for distributing policies in the runtime, you talked about getting this OPA calls to the applications that are running. How about distributing like the model or the permissions that are based on dynamically updated user attributes or roles?
Yep.
Right?
Yeah, that's a good question. So the question is basically how do we distribute data to OPA?
Yeah, and how do we avoid actually incurring that on-network copy?
Yeah, yeah. That's a good question because what we always want to avoid is like going to an external source and fetch data at the time of a policy evaluation. So the common way of doing it is normally that OPA polls an external endpoint asynchronously for updates to policy and data, and then it fetches those as soon as it's made available, and it stores it and it kind of updates whatever it has in memory. So that's done asynchronously, and it's not done at the time of the decision. But of course, it does mean that there could be a few seconds of delay where it's like, if this data is updated now and you want that reflected immediately, you probably need to do that network call. But for most deployments, like permission data is modified, I don't know, like basically never. You just have a role. That role means this or that. But there could be new endpoints added, new resources and whatnot. But for most applications, that kind of a small delay in updates to data is fine. But if you need kind of real-time availability on data, then you're going to have to work with some other models.
Are there competitors to OPA, or the only alternative is?
Yeah, that's a good question. Are there alternatives to OPA or competitors? Yeah, for sure. So there's a few competitors or alternative ways of doing authorization. There's of course a few competitors or alternatives doing admission control. There's a few doing infrastructure as code and whatnot. But I'm not aware. What I'm not aware of is any alternative for doing policy across your whole stack. So it's basically one of the premises of OPA, and why I really kind of like working with this. It's like it's so diverse. You have one way of describing these rules across your whole system. Once you invest the time, and for sure it's a learning curve as with anything. But once you know, like you have one way of describing rules whether it's access control, whether it's infrastructure, whether it's Kubernetes, whether it's your GitHub Actions or your Jenkins server. Anywhere you have rules, you have one way of describing them. And you have one way to log decisions. You have like a unified way of working with policy across the whole stack. And for that, I am not aware of any competitors, but I'd love to see one because the more the merrier, and we can all learn from each other.
Since you now have the immediate representation, are there any alternatives to Rego for defining the policies? Say you have an existing system with policies defined out. Right? You can export it as JSON or something like that.
Yeah, that's an interesting idea. So the question is, since like the IR representation, it's no longer Rego. It's just, can we use some other language to generate that? And yeah, we could. I'm not aware of any implementation to do that, but that could be an interesting topic to explore. That's for sure. All right, I think we're running out of time. Thank you very much.